Okay, so welcome to the 8th week of problem solving section for the course Availability and Management of Groundwater Resources. We'll be discussing topics on measurement of rainfall, index of wetness and infiltration rate based on the lecture that was taken during the 8th week. As always, I'll be showing some questions in the slides, and you will have to put in the answers in the chat box, and based on that we'll discuss the solution. Moving on to the first question. Which among the following method is very accurate for rain gauging? Arithmetic mean method, season method, isohydral method, or recording type? Please put in your answers in the chat box, and then we'll move on to the solution. The question is, which among the following method is very accurate for rain gauging? Okay, so moving on. Let's see what all are these methods of finding out the mean average rainfall. So here they've mentioned about 4 methods: arithmetic mean method, season method, isohydral method, and recording time. So let's see what each of them are, and then we'll see which is the correct answer. So we all know what a drainage basin is, and we also know that in order to get how much of rainfall is occurring in drainage basin, what is usually done is the drainage basin is divided into certain sub basins, and each sub basin, a rain gauge is kept in the sub basin at a particular station, which is called the rain gauge station. Now each rain gauge stations will be having rain gauge, which is an instrument used for measuring the rainfall occurring. So when we have so many values of rainfall, how do we find out what is the rainfall for the entire basin? It is done by finding the average rainfall over that entire area. So in order to find the average rainfall or mean rainfall for a particular drainage basin, the methods, few methods suggested here are the arithmetical mean method, which is the first method. So this is a very simple method. Nothing is done. For whatever rain gauge stations are there in the drainage basin, all the values of the rainfall in these rain gauges placed in these rain gauge stations are considered, and it is average. That is total number of rainfall. The total rainfall that is collected in each rain gauge station is summed and divided by the total number of rain gauge stations. This is called the arithmetical mean method, and it's a pretty simple method. Now the next method is called the Thiesen's polygon or Thiesen's mean method. In this, what is done is if this is a rain gauge station, if this is a base in the place a point down. So if see here, this irregular polygon is the drainage basin. Then, and if these dots that are numbered 1, 2, 3, 4, and 4, 5, and 6 are the rain gauges in inside this basin, then what is done is all these rain gauges are connected together to form triangles. You can see here 1, 2, 3 are connected to form triangle. 3, 5, 4 are connected to form triangle. 3, 1, 5 is connected to form triangles like this. Now, after the triangles are created, the perpendicular bisectors of the sides of this triangle are created. Now, once the perpendicular bisectors of the triangles are created for all of these triangles, a polygon like this will be obtained by joining all of the perpendicular bisectors. This polygon is what you call as a Thiesen's polygon. So again, saying one more time, the entire basin is considered. The the rain gauge stations, each of the rain gauge stations. Now you can see there are few 3 and 6 are coming, 3, 6, 5 are coming outside the drainage basin. So this is again making the results more accurate because it is also taking into consideration the adjacent areas adjacent to the drainage basin. So the rain gauge stations in each of these inside this basin is connected, and triangles are formed, and these perpendicular bisectors of these triangles are found out. So you can see here the perpendicular bisectors are found out. Similarly, here also the perpendicular bisectors are found out. So for each triangle, the perpendicular bisectors are found out, and polygons that are formed as a result of the polygons formed as a result of these bisectors are called as Thiessen polygons. If you look at this table over here, we know that the station 1, 2, and 3 connected have perpendicular bisectors, and D is the perpendicular bisector for, I mean, D is the joining point of the perpendicular bisectors. Now, if you see say, this triangle, G is the perpendicular bisector of this triangle. Now G and this point C and B, wait, this is E. So E, B, C, G, and F is forming one polygon. So you can see here C, D, E, G, and F are forming one polygon. And that polygon, say it has got an area A3. The weightage of that area will be A3 by A. If the entire basin's area is A, then the weightage of this area will be A3 by A. Now using this formula, the Thiessen's polygon method formula, A1, P1. A1 is the polygon area, A2 is the polygon area, A3 is the polygon area. P1 is the rainfall in the station that is marked as 1. Then finding out the sum of the product of these two values and dividing it by the entire area will give us the mean rainfall. So this is how Thiessen's mean method is used. It is taking into consideration the area and giving some weightage into the area of the basin also, unlike the arithmetical mean method. Now, the third method is the isoheightal method. Now, isoheightal method, in this method, the word isoheight is nothing but it is a line that is connecting a contour line that is joining rainfalls of equal magnitude. So, isoheight will look like this. Suppose there is a drainage basin like this, and there are so many rain gauge stations. Each rain gauge stations have a particular value, say 9.5, one has 10, one has 11. Then all those points that has got 10 as the rainfall magnitude are connected. All those points that has got 11 magnitude are connected, and a line is drawn, like how we draw the contour line for same elevation. So these lines are called isoheights. Then once these isoheights are found, the area between these two isoheights is found out by using a planimeter, and then this equation is used. The P1, P2, that is value of the precipitation between the two isoheights. Now, suppose we are considering the area between the rainfall where the value is 10 and 11, then P1 is 10, P2 is 11, and the area is this one. So P1 plus P2 by 2 into the area that is corresponding to these two isoheights, and sum of all of that divided by the total sum of the area will give us the average rainfall. So these are the three major methods in which mean rainfall or average rainfall is found out. And the question here is, which among the following is the most accurate? Excuse me. The correct answer is the Thiesen's method. And the most simplest method is the arithmetic mean method. Recording type is not a method. It is just a recording type rain gauge station, which we look in the further slides that are yet to come. Now the second question, which of the following is a non-recording gauge? Is it Simmons gauge, tipping bucket type, weighing bucket type, or natural siphon type? Okay, let's move on to the answer. So rain gauges basically are of two types. One is the non-recording type, and the other one is the recording type. So non-recording type, as the name suggests itself, is those rain gauges where no recording of the values are taken. There's some device to collect the rainfall that is occurring, and only after the jar is full, it is measured separately. The how much rainfall and happened in that area is recorded separately. There's no at the time of in the machine there is no recording device. We are measuring the rainfall after um, weighing or seeing how much depth of the water is obtained in the collecting bottle. Whereas recording type rain gauges are ones where there's a mechanism to record the value of the magnitude or the depth or the weight of the rainfall while it is being collected in the collecting device itself. Now, as you can see here, um, one of the non-recording gauges is called the Simmons gauge, which has got a circular collecting area of 12.7 diameter, zero point 0.7 centimeters diameter, and a height of 30.5 centimeters. You can see there's a collecting bottle in here and a funnel through which the water will fall and will get collected in this collecting bottle. And this water content of this collecting bottle will be measured. And in the recording gauges, the major three types of recording gauges that we're talking about here is the tipping bucket type, weighing bucket type, and the float recording type or the natural siphon type. These are the three types of recording rain gauges. So the question here is, which of the following is a non-recording gauge? The answer would be A, Simmons gauge, the tipping bucket, weighing bucket, and natural siphon type or floating type rain gauges all are recording gauges, these three, B, C, and D. Moving on to the third question. Vegetation affects the runoff. Is this statement true or false? Okay, so the answer is true. We know that when runoff is happening and there's crops around or there's crops that is restricting the flow of the water on the surface, then obviously the runoff will be affected because of the vegetation of plants that are on the way of the water flowing. So it will affect the runoff. Which type of rain gauges are used by the US Weather Bureau? So let's look into what the answer is. So let's see what tipping bucket type other types of devices are which have been mentioned here. They're talking about Simmons gauge, tipping bucket type, weighing bucket type, and natural siphon type. So we learned that Simmons type is the non-recording gauge. Tipping bucket type is a recording gauge. So as the name suggests, it has a mechanism where using a funnel, the rain that is falling is flows through this funnel into a small bucket. This bucket as long as the rainfall collected is up to 0.25 mm, the bucket will keep collecting water, and once exceeds the 0.25 mm of water, it will tip. It will get upturned, and it will put push the water into this in below it. So what happens is there's a recording device that is connected to this tipping bucket, and for every 0.25 mm, when the tipping is happening, the recording device is activated, and it will record at what time this 0.25 mm of water was tipped. So it is based on this mechanism that the tipping bucket type works. And recording type, because there's this pen that is attached to this tipping bucket, electrically driven pen, which is plotting the intensity, that is 0.25 mm of rainfall is when it tips, it knows that 0.25 mm of rainfall has occurred. So 0.25 mm of rainfall within how much time is occurring will be recorded by this device. Then so this is the rain gauge that is used generally by the US Weather Bureau, the tipping bucket type. So the correct answer for this question would be option B. Now, fifth question. Rainfall is also known as what? Downpour, precipitation, condensation, or infiltration? Okay, so the correct answer is option B, precipitation. Downpour is nothing but if when water is falling down, we say it's I mean, it is also a very casual way of stating rain, but the proper term used for rainfall, snowfall, etc. is precipitation. We know what condensation is. Condensation is when water changes from vapor to its liquid phase, and infiltration is the movement of water through soil. So the correct answer for this question would be option B, precipitation. A flow chamber type catch is used in which of the following type of gauge? A flow chamber type catch is used in which of the following types of gauge? Is it in a tipping bucket type, weighing bucket type, a natural siphon type, or non-recording gauge type? So let's see what all these are. We learned about what a tipping bucket is. We also just briefly looked into what a Simmons type rain gauge is. So let's see what weighing bucket is. Now, similar to a tipping bucket, collecting 0.25 mm of rainfall and tipping when 0.25 mm of rainfall is collected in the bucket. This weighing bucket type, what it does is there's a funnel. Through the funnel, the water will enter this bucket, and this bucket will keep on collecting the water. And the bucket is attached to a mechanism where the weight of this bucket is measured. So this is where the pen will be connected to. So the weight of the bucket is recorded with time, and this is how the recording mechanism is in a weighing bucket type. And just like the name suggests, in weighing bucket type, the weight of the water is measured, which is used as a reference for understanding the amount of rainfall. Whereas in a tipping bucket type, the bucket 0.25 mm of water, as soon as it is filled, it will tip, and that is what is the recording mechanism attached to. Then in the natural siphon, or it is also called the float type recording gauge. Again, like the name suggests, there's something associated with float. So here what happens is inside this chamber, water will be collected and there's a float attached to it. So once this float reaches a particular height, so as the water keeps filling, the float will keep raising and raising, and once it attaches the particular level, the water will be drained out from the siphon tube. So it is attached to this, that recording device will be attached to this float, and based on this movement of the float, the rainfall measurement will be done. So in this natural siphon type, the recording device is attached to a float which will keep on raising as the rainwater gets collected, and once a level is reached, the water will be drained out using a siphon, and this recording device is attached to the float type. In weighing bucket type, it is attached to the weight of the bucket, and how much of water is getting accumulated by weight is what is being measured in the weighing bucket type. In tipping bucket type, the bucket is tipping, and it's based on that the recording is done. So these are the three major types of recording devices. And Simon's gauge, earlier I said, there's a collecting bottle that will collect the water, and after the water is collected, that is from one particular time to another particular time, water is collected, and that total water is measured using a measuring jar. So the time, that is time starting and ending time, that is used for measuring the rainfall is 8:30 a.m. in the morning till 8:30 a.m. in the next day. So 24 hours of reading is taken using this collecting bottle. Again, the collecting bottle, it cannot hold more than 10 centimeters of rain. So frequently the water frequently the water will need to be removed from the collecting bottle, and then recorded. So this is how a non-recording type rain gauge works. So here the flow chamber type catches used in which of the following type of gauge? The correct answer is the floating type or the natural siphon type. The option C will be the correct answer. Okay, moving on to the next question. Intensity of rainfall is measured by continuously recording gauge, an anemometer, hydrometer, or a seismometer. Yeah. So the correct answer is A. We know that the recording gauges is what is helping in measuring the rainfall. The other options, anemometer is used for measuring wind speed and wind pressure. Hydrometer is used for measuring the characteristics of liquid, like its density and specific gravity, And seismometer is used for measuring to record earthquake movements. So the correct answer for this question would be option A. Moving on to the eighth question. When annual rainfall is greater than the average annual rainfall, what is it called? Is it called a good year, a bad year, a very good year, or a very bad year? Okay, so before we know what is called as a good year or bad year, let's see what is the difference between an annual rainfall and what is an annual rainfall, what is this annual rainfall, what is this average annual rainfall, and what is the difference. So average annual rainfall, uh, we know that if the amount of rain that is collected in 24 hours is giving us the rainfall of a particular day, that amount is called the daily rainfall. Now, the rainfall that is collected for an entire year, that is what is called as the annual rainfall. So, if for 10 years, if you're asked to take the data for 10 years, we'll take the data for the first year, we'll take the data for the second year. So, first year's annual rainfall, second year's annual rainfall, third year's annual rainfall, and 10 years of annual rainfall. Now, when the annual rainfall is measured, and one rainfall cycle in India, particularly one rainfall cycle is considered as one rainfall cycle period for whatever measurements or comparisons or probability. The standard period for considering the rainfall cycle is 35 years. So when we collect the yearly data, annual rainfall for 35 years, and find out the average of the rainfall in 35 years, then that value is called the average annual rainfall. So the rainfall that is collected, annual rainfall value that is collected for each year is averaged, and the value that obtained is called the average annual rainfall, or another term that is used for it is the normal rainfall. So average annual rainfall is nothing but the average of the annual rainfalls that is collected for a particular 35-year period. Now, when we compare this annual rainfall with the average annual rainfall, then the index that is coming as a result of finding the ratio of the annual rainfall to the average annual rainfall is called the index of wetness. So the relation of the actual rainfall that is happening in a particular year, which is the annual rainfall, and the average annual rainfall is called the index of wetness. Now it is based on this that we can say that, say if we are getting 5 centimeters of rainfall for a particular year, but the average annual rainfall that we're getting as a result of 35 years of data historically is 10 centimeter, then 5 by 10 is the index ratio. Now, if the annual rainfall is less than the average rainfall, say annual rainfall is 10, and if the annual rainfall is only 5 centimeter in a particular year, then we say that that year is bad in terms of the amount of rainfall that is obtained. Now, if it is almost equal to the average annual rainfall, then we say that it's an average year. It has got the average rainfall. And if it is greater than that, then we say it's a good year. And similarly, the deficiency also is calculated like that. So if the 60% index of wetness, it means it is 40% deficient. So if the deficiency is 30 to 45%, we say it's a huge deficiency. If the deficiency is around 45 to 60, we say it's very serious. And if the deficiency is greater than 60%, we say it's disastrous. You can say that uh, the 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 drought condition can arise as a result of this deficiency. So this is what is annual rainfall, average annual rainfall, index of wetness. So it is based on this that we say it's a bad year, a normal year, or a good year. So the answer for this question would be, if the annual rainfall is greater than the average annual rainfall, then it is called a good year. It's good year, normal year, or bad year. There's nothing like very good year or very bad year. So it's option A, good year. Okay. Now the ninth question. As per IS recommendation, the rain gauge density for plain region is given by one station per 520 kilometer square, one station per 620 kilometer square, one station per 260 kilometer square, or one station per 130 kilometer square. What is the range gauge density for plain region as per the IS recommendation? Okay. So let's see what this rain gauge density is. So rain gauge density is nothing but what is the number of rain gauges per square kilometer area. So for in 1 kilometer square area, how many rain gauges are required is what is called the rain gauge density. Now this density, that is how many number of rain gauges are required in a particular basin, in a particular sub basin, in a particular area, is defined by a lot of factors. One of the factors is based on the terrain of it. Now, as per IS, terrain means what kind of a topography that area is called. Is it a steep area? It is a plain area? It is a hilly area? What type of area it is what is one factor determining the number of rain gauges to be kept in a particular area to record the rainfall. So, as per IS recommendation, based on the terrain, the recommendation for rain gauge density is 1 for every 520 kilometer square. So for in plain regions, every 520 kilometer square requires only one rain gauge. Now, in regions where the average elevation is around 1000 meters, then we might need a rain gauge station for every 260 to 390 kilometers square. And similarly, when for a region which is very hilly and there's so many, the rain is very heavy in such regions, for such areas, you will require a station for every 130 kilometers square. So once again, rain gauge density is nothing but the number of rain gauges per square meter area. And as per IS recommendation, the rain gauge density for plain area is for every 520 kilometers square, you require one station. When it comes to areas with average elevation around 1000 kilometers square, you require 260 to 390 kilometers square, we will require one station. And if the area is a hilly area with heavy rainfall, then we will require one station for every 130 kilometers square. Now, how if we have area, we suppose we have a huge area of, as you see here, 5200 kilometers square. And how do we know the number of rain gauges that we require to keep in 1 kilometer square? Can be obtained by dividing 520 by 5200 by 520. So the entire area will require 10 stations. So every kilometer square, you will have to keep one station. So the entire 5200 kilometer square area will have 10 stations. So this is the importance of, this is how a rain gauge network is formed, and importance of rain gauge density when it comes to the type of terrain available. So the correct answer for this question would be A. The question asked is the rain gauge density for plain region. It is one station per 520 kilometer square. Question 10. There are 4 rain gauge stations existing in the catchment of a river. The average annual values at these stations are 800, 620, 400 and 540 millimeters. What will be the mean rainfall? So we studied about various methods to find out the mean rainfall. Since this no method that is specified for which we have to find out, and also there's no area that is given and only the number given. Make use of the appropriate equation to find out what will be the average rainfall. Okay. So the method to be used here will be the arithmetical mean method, where you'll just add all these numbers and divide it by 4. Since, like I said, there's only the number of rain gauge stations and the values at each rain gauge stations that are provided. There are no values of the area that is provided. So we have just from the data available, we can only find out the average of these values. So the average of these values 800, 620, 400, and 540 would be 590 mm, which will be the correct answer. Option B will be the correct answer. Now, question 11. Which of the following rain gauging method is consists of a contour joining the points of equal rainfall? Which of the following method is a contour that is formed as a result of joining equal rainfall obtained? Is it in the arithmetical mean method, the Thiessen method, isoheital method, or the recording type? Okay. So we know what the isoheital method is. Isoheital method, like I explained earlier, isoheights are formed. Isoheight is nothing but contour lines or line connecting points of equal rainfall. And the area between two isoheights is measured, and the product of those two areas divided by the sum of the product of those two areas. This is a formula for isoheightal method. Using the formula, that is giving some weightage for the area also is considered for finding out the mean rainfall. So some important points you can you can keep in mind with regard to the isoheids is that different isoheids are not going to cross each other. Isohedral methods, isoheids are formed in such a way. Then each isoheid will close on itself. The basin there, when the isoheids are it will be measuring from one point to the another, and there is no requirement to cut off the isoheids by any other line. Then isoheids of higher value indicate higher rainfall. That is obvious. The next question: what is a hydrograph? What kind of plot is a hydrograph consisting of, or what type of plot is a hydrograph? Is it depicting cumulative rainfall versus time? Is it depicting rainfall depth versus duration, or rainfall intensity versus time, or discharge versus time? Okay. So this is what a hydrograph is. It is a plot of the intensity versus time. So rainfall intensity it will keep increasing until it reaches a maximum value and then keep decreasing. So this plot where rainfall intensity is versus time is plotted in the following way is called the hydrograph. So the option C would be the right answer. It's third option, rainfall intensity versus time. Discharge versus time is called a hydrograph. I think we discussed about this in the last session. The others we'll be looking in the further stage. What is the plots called for the subsequent representation. Now, the rainwater in the gauge shall be measured every day at what time? What Indian Standard Time? This also we had looked into. Hi Snehal, if you know the answers of this question, you can put it in the chat box and then we'll discuss the solution. Okay, so the rainwater is measured every day at 8:30 a.m. in the morning, and then the starting time will be 8:30 a.m. and it will be measured. The values will be considered until next day 8:30 a.m. So the correct answer for this question would be first option 8:30 hours. The rainwater in the gauge is always measured from 8:30 a.m. to the next day 8:30 a.m. Now, this is a numerical. A catchment has 5 rain gauge stations for a 6% error in estimation of mean rainfall, and coefficient of variation for these rainfall values is 20. Determine what is the number of stations required. Okay. So this is based on the optimum number of rain gauge stations, the formula based on the optimum number of rain gauge stations. Let's just see what it is. So optimum number of rain gauge stations is the uh, uh, an area should always require an optimum number of rain gauges. So how do we find that? We find it using some statistical measures have been taking care of how what will be the number of rain gauges that have to be in one area based on the error of the rainfall that can occur and errors in the calculations that can occur. This formula has been formed, and this is the value n over here is giving us the optimum number of rain gauge stations required in a particular area. CV is the coefficient of variations of rainfall that is based on the existing values that is obtained from rain gauge station. So the values of precipitation that is obtained from rain gauge station, coefficient of variation is found out, of the coefficient of variation of all those values is found out. That is what is depicting CV. E is the percentage of error that is allowed while estimating the mean rainfall. So the optimum number of rain gauges is found using CV by E the whole square. So in this question, they have given the number of rain gauges is five, and the error that can that the error that is okay enough to come during the calculation of the rainfall is 6%, and coefficient of variation is 20. So number has been given for 5 rain gauge stations. So optimum number of rain gauge station can be found out by using substituting these values directly in this formula. It is 20 by 6. Coefficient of variation is CV equal to 20, and percentage error you have to input it in the percentage value itself. So 20 by 6 the whole square will get 11.11, and we see that the optimum number of rain gauges required is 12. Now, they have asked what is the additional number of stations that is required. They've said that there is 5 stations, but we want to know what is the correct amount of stations that is required in that area, and it is 12. So now, how many more rain gauge stations will we have to keep in there so that that area has got sufficient amount of sufficient? The correct word would be optimum. It's not too less or too more, too high. Up to the number of additional stations that will be required is the optimum number minus the existing rain gauge stations available, which is 7. So this is how you make use of the optimum number of rain gauge stations, the formula, in order to find out what is the optimum number of rain gauge stations that is required in one area. And not only that, if the question or if the problem is there are some rain gauge stations, but we want to know based on the optimum number of rain gauge stations, how many more rain gauge stations we need to install in a place so that proper amount of rainfall can be collected for the correct calculation. Again, this is based on the same thing. The coefficient of variation of 6 rain gauge station is found to be 29.54. The optimum number of rain gauge stations for a 10% error will be what is the question. Same formula, using the same formula, you can find it out. Okay, so let's again check the solution. So these are the formulas for finding out what is the coefficient of variation and how we find out the coefficient of variation. So like I said, a coefficient variation of the mean rainfalls that is given. Existing 6 gauges are given. And how do we find out the coefficient of variation if the CV value is not given is? We will find out the standard deviation. Again, the formula used in standard deviation is that value. If xi is the value of rainfall in a particular rain gauge station, we will find out the mean value of the rainfall. xi minus x bar the whole square by n minus 1 the whole root will give the standard deviation. Now that standard deviation by the mean will give you the coefficient of variation. So making use of this, if suppose the coefficient of variation is not given, making use of the standard deviation equation and coefficient of variations equation, we can find out what is the coefficient of variation, substitute in this formula and find out the optimum number of rain gauge stations. Optimum number of rain gauge stations. Now here already the rain gauge optimum number has been given. So I mean, sorry, the coefficient of variation is given. So we don't have to make use of this formula. But in some problems, what they do is they give us the individual. That is, they say that 6 rain gauge stations are already there. Their rainfalls are P1, P2, P3, P4, P5, P6. What is the optimum number of rain gauge stations required if the error is supposed to be this? Then we'll have to make use of this formula to find out the standard deviation. We'll have to divide it by the mean and find the percentage of it, which is giving us the coefficient of variation. Then substitute in this formula and then find out what is the optimum number of stations. So again, this is the formula for finding out what is the allowable degree of error. If you have the coefficient of variation, I don't know why they have found this out anyways. Okay, if okay, if we have the number of rain gauge stations that is given to us, we need to find out the error. Then we can find it out using this. So we have the number of rain gauge stations that is given over here as 6 already. So I don't think so. We need to make use of that equation. We just have to find out, put in 29.54 divided by 10, the whole square. It will be 2.95, 2.95 the whole square. And then that will give us the value of optimum number of rain gauge stations. 9 minus 6 will be the additional rain gauge stations that is required to be kept in that station. But here they have only asked us to find out the optimum number of stations. So we don't have to find that minus the existing stations. We just have to find out this value. Now the 16th question. What is called the mass curve of a rainfall? What kind of a plot is this mass curve of a rainfall? Is it a plot between the accumulated precipitation and time in the chronological order? Or is it the accumulated rainfall intensity versus time graph? Or is it rainfall intensity versus time in chronological order? Or is it none of these? Okay, so the mass curve of the rainfall is nothing but it is a plot between the accumulated precipitation versus time in the chronological order. Chronological order is nothing but what comes a plot, that is you order it in such a way that the first value will be the rainfall that has occurred first until the later time. So what is the rainfall that occurred in the first day, the second day, the third day, fourth day? All the rainfall values will be arranged in that order, and then the accumulated rainfall will be found out, and that will be plotted together versus time. And such a graph is called the mass curve of rainfall. Now, in recording type rain gauges of natural siphon type and the weighing bucket type, the recording done is a mass curve of the rainfall. That is a plot that we obtain as the output from this recording gauges. So the mass curve of a rainfall of a storm is plotted between accumulated precipitation and time in chronological order. Option A will be the correct answer. The 17th question, if the intensity of rainfall is more than the infiltration capacity of soil, then what will the infiltration rate be? Will it be equal to the rate of rainfall? Will it be equal to the infiltration capacity? Will it be more than the rate of rainfall, or will it be more than the infiltration capacity? Okay. So in order to know what the answer of this question is, we need to know what the intensity of rainfall is, what is the infiltration capacity, what is the infiltration rate, and all such terms. So let's see what all of these are. So we are aware about what infiltration is. Infiltration is the process in which water, when it reaches the ground surface, will flow into the soil to the subsurface of the soil. Now, this water that is flowing into the surface of the soil, through the surface of the soil, is flowing with a particular rate. A rate is nothing but how much of depth is covered in particular time is what is called the rate of infiltration. Now, when we say rainfall intensity, it is nothing but the rate, that is how much of rainfall, what is the centimeters of rainfall occurring in 1 hour, or what is the centimeters of rainfall occurring in 1 second, is what gives us the rate or intensity. Rainfall intensity is nothing but the rainfall rate occurring. So infiltration is also occurring in the same way. Infiltration also, there's a rate with which the water is flowing into the soil. Now, that is what is infiltration rate. When you take a particular sample of soil, pour water, the rate with which water is flowing through the soil into the subsurface of the soil for that particular soil in a particular amount of time is called the infiltration rate. Now, what is infiltration capacity? Infiltration capacity is the maximum rate that can exist in that soil. So that particular soil at a particular time, because of its properties, it will only be able to absorb the water at a particular rate. Beyond that rate, it will not be able to, the water will not be able to enter into the soil in a rate more than the infiltration capacity. So infiltration capacity is nothing but the maximum rate at which a soil can absorb water. A given soil at a given time, what is the rate, maximum rate with which the water can enter the soil is called infiltration capacity. Say if the infiltration capacity is 2 centimeter per hour. So in 1 hour, that soil sample, the in 1 hour only 2 centimeters of water will enter the soil. Say if there is a rain occurring and that rain is occurring at 3 centimeter per hour, then even if the rain is occurring at 3 centimeters per hour, only 2 centimeters of water will enter the soil in that 1 hour. The remaining 1 centimeter, it will stay back on the surface itself. It is not going to be able to come down to the soil. So infiltration capacity is the maximum rate a given soil at a given time can allow the water to enter. Now, that is a maximum rate. There is a particular rate with which water will enter. It is not always going to be in the infiltration capacity. It will have a value which is equal to the infiltration capacity, or it can have a value which is lesser than the infiltration capacity. That rate of water at that particular time, what is the rate with which water is flowing inside the soil is called the infiltration rate. Now here the question that was asked is, what will happen when the rainfall is, the question is, what if the intensity of rainfall is more than the infiltration capacity of soil? So when rainfall is occurring at a rate that is higher than the infiltration capacity of the soil, then water will only, that much water, That is, if it is 5 centimeters per hour is the intensity of rainfall and the capacity is 3 centimeters per hour, water will only be able to enter at 3 centimeters per hour maximum. The 2 centimeters of hour will stand on the surface itself and it will flow off as runoff. So when it comes to the infiltration capacity, the intensity of rainfall, 3 conditions can come. If the actual rate of infiltration, that is, at that time, what is the rate of infiltration, is such that if it is depicted by the letter F and Fp is the infiltration capacity, then if the intensity of rainfall I is greater than the infiltration capacity, then the amount of rainfall will occur and the infiltration rate will be equal to the infiltration capacity. Now, if the infiltration rate is less than the infiltration capacity and if the intensity of rainfall occurring is also less than the infiltration capacity, then whatever water is reaching the surface, it will seep into the soil. That is, it will infiltrate into the soil. So associated with the infiltration rate, rainfall intensity and infiltration capacities, this comparison or this conditions is something that you have to keep in mind. So the correct answer would be if the intensity is more than the infiltration capacity, then the infiltration rate is going to be equal to the infiltration capacity. Option 2 will be the correct answer. Question number 18. The Horton's infiltration capacity is given as. So there are various kinds of formulas that will help in estimating the infiltration capacity of a soil. One of the formulas is Horton's infiltration capacity. What is the Horton's equation for finding out the infiltration capacity out of the following? Let's see. So infiltration capacity can be estimated using certain mathematical expressions like the Horton's equation, which is the question that has been asked right now. The Phillips equation, Kostyukov's equation, Horton's equation. So these are some of the methods or mathematical expressions for finding out the infiltration capacity. Then the Horton's equation is this. It is giving the infiltration rate at a particular time as a function of the minimum infiltration capacity and the initial infiltration rate, a constant K, which is depending on the soil type and the vegetation cover and the time T. So this equation Fc plus F naught minus Fc to the power e power minus Kt. Here Fc is the minimum infiltration capacity. F naught is the initial infiltration rate. E to the power minus Kt. Here K is a constant based on which the case 1 where the constant that takes into consideration the soil type and vegetation cover where the infiltration is occurring, and T is the time at which we want to measure the infiltration. That is when is the infiltration, what is the infiltration occurring when a rainfall of a particular intensity is happening. That is what is T. So that we can find out using this Horton's equation. And Horton's equation follows such a curve, this form, where this is Fc, the minimum infiltration capacity. Then F naught is the initial infiltration rate. Infiltration rate, minimum infiltration rate occurring, initial infiltration rate occurring. This is the infiltration capacity curve at a particular time, if we require to find the infiltration rate, then from this curve we can find out what the infiltration rate is at a particular time. K will take care of the type of vegetation and soil type. So it's based on this, the infiltration curve is also going to vary. So the correct answer is option 4. F is equal to Fc plus F naught minus Fc into e to the power minus Kt. Option D will be the right answer for this question. Cotton's infiltration capacity curve. So that's all for today's 8th week of problem solving sessions. If you have any doubt regarding the questions that have been discussed now, please feel free to ask, else we can end the session. So I don't see anyone has any doubts regarding the session. So thank you for attending today's session. We will see next week with the session of problem solving session on question based on the 9th week's lecture. Thank you so much and have a good weekend. See you next week. Bye bye.